And welcome to today's well, my evening, but other people's mornings session. And we'll have two talks here, and we'll start with Marta, and I'll be, as I said, giving you a 5-minute warning.
Okay, now I think you can hear me. Good, thank you very much. And thank you also to the organizers for having me here and for allowing me to discuss with all the exciting science that has been presented in the last few days. So what I will try to do today is to connect a little bit what we can learn about local black holes with their general cosmic evolution. Angelo Ricarte on Monday already gave a good overview of all this, so I will mostly build on what he has briefly mentioned then. So I'm sure that most, if not all, of the people present here are familiar with M87, the black hole in the galaxy M87, and Sagittarius A star in our own galaxy. But in the local universe, we have at this point information, although not as detailed as for these two black holes, on hundreds of black holes, really. This is shown here is a small compilation of nearby local black holes. So over the years, we have learned that black holes power active like nuclei and quasars, but some of them are quiescent. Again, Sagittarius A star is the best example of a quiescent black hole that we have. They generally habit in the center of nearby galaxies. In most cases when a black hole was looked for, it was found. And as you see here on the y-axis, which is the black hole mass, they really span a very wide range from a little over 10 to the 4 solar masses to more than 10 to 10 solar masses. In this figure, the x-axis is the stellar mass of the galaxy. And as you see here, large black holes live in large galaxies, or massive black holes, the heaviest black hole live in the heaviest galaxies, and vice versa. So this hints to a coevolution, a growth of galaxies and black holes over the cosmic history. Since we know that galaxies, the stars in many of these galaxies, especially the massive ones, are very old. Black holes must have grown with galaxies over the same time scale, so about 13 billion years. In this figure, again, as I said, these are local black holes. Already some very important questions come to mind, and where ngEHT could help. Here you see this, in this figure, not all black holes are equal, in the sense that different techniques can be used to measure black holes in different galaxies, depending on how close they are, what type of emission you have. And so while for the Milky Way and some AGN with Blazars, and here Chung-Pei on Monday gave a very long review, so I will not say much more, you can have excellent mass measurements. As you move to other galaxies, the techniques become less and less reliable as you go farther away, or if you target active black holes. Particularly, for instance, reverberation mapping is a very powerful technique that gives very good information on black hole masses, except that it needs a normalization factor that is a priori not well known. So having a way to calibrate mass measurement relations, as EHT has done for M87, would be very important for people working in this field, so that we could improve our understanding of black hole galaxy relationships. So we will limit our unknowns on the position of black holes on the y-axis here. But also something that is not often mentioned is that having a good measurement of, or a reliable measurement of black hole masses is very important to measure the Eddington ratio, which is the ratio between the luminosity of an AGN and its Eddington luminosity, which is an indication of how effectively a black hole is accreting. For all but very quiescent black holes, the techniques that we use to measure black hole masses don't allow sufficiently high accuracy to actually have good Eddington ratio measurements. And this is true especially for higher distant quasars. And so this is a problem in the sense that we cannot really know how fast black holes are growing. And so again, this depends significantly on a calibration that has to be done on local black holes. And hopefully ngEHT will, adding more black hole masses will help with that. But besides, the very local universe, when we go and look at farther away, how do black holes and galaxies grow from the early universe when both of them were small to today? I mean, this is a question that I've been having fun addressing for many years now, and it's still not answered, and we have many uncertainties. And so I will connect here some of what we know about black holes to the questions that at least I hope ngEHT can help answering. So let me start with a movie. This is from Michael Tremel, and shows a cosmological simulation of a galaxy about the same mass as the Milky Way. Here you see dark matter shown in blue. Green is gas. You see stars forming. The stars form blue and then they turn red as they age. But also here you see these white dots, and very shortly you will see many more. And these white dots, although they're white, they're actually, poof, you see there, black holes, massive black holes that form in the simulation. And from their formation, they start and evolve with galaxies over, as I said, about 12 to 13 billion years, depending on the time when they form. So here you see that there is really everything evolves at the same time: dark matter, gas, stars, and black holes. And removing black holes from this picture would significantly change the properties of galaxies. Now we know that they're really an integral part of the evolution of galactic structures. So here you see the cosmic dance of black holes. This is how I normally describe it. Typically in galaxies, you have more than one black hole, and these black holes are orbiting, depending on the orbital parameters that they inherited during the merger between two galaxies with black holes, at different distances with respect to the center. At this point, you see that as the galaxy has changed structure, now you see a central bulge dominated by old stars. You see young stars here in the disk. You see the formation of the galactic disk. And in all these, black holes have merged, black holes have accreted gas, they have grown in mass, they have injected energy as they produce radiation and thermal, kinetic energy, various forms of energy from jets to disks. And all this is how we see the evolution of galaxies and black holes over time. So here we have reached today, or something like that. If you give it to take a few billion years, the galaxies formed, the black holes have formed. And so we have connected from a messy, initially very dynamic universe to something that is more quiescent, and now we can measure the properties that have at the moment. The one thing that we know is that black holes must have grown significantly over time to become what we see today. Now, in this figure, I compare the distribution of different types of black holes. So here we have stellar black holes, so just the endpoints of massive stars. Here we have massive black holes, again, with some famous ones, Sagittarius A star and 87, and GC25 is the lowest mass black hole candidate that we have in terms of massive black holes. GW190521 is the largest black hole, the most massive black hole that was detected by LIGO Virgo. And here in this square plus the two arrows show where with the mass and number density range where we think that black hole sits. formed in the first place. And you start from these states forming in galaxies, or perhaps even before galaxies. And then all these black holes must grow significantly in mass if we want to explain black holes like M87, because no black hole at birth, we don't, at the moment, I don't think that we have any reliable, trustworthy model that predicts the formation of black hole of above 10 to the 9 solar masses all of a sudden. So how this evolution from small light black holes at high redshift to today is really how all this combines with galaxy evolution to create the universe as we know today. Now, in terms of black holes, massive black holes, the growth of these systems can happen through two main channels. One is merging with another black hole, and one other is accreting gas. During gas accretion, you form an accretion disk, and in this case, a black hole would be active and seen as a quasar using our telescopes. But interestingly and luckily for us, we could also witness the growth of black holes through galaxy mergers, because in that case, they emit gravitational waves that are invisible to our telescopes, but can be detected with gravitational wave detectors. So black holes, in some sense, have really a way of telling us when they're growing in mass, either by merging with other black holes or accreting gas, but in any case, they will make themselves thin, known at the time. So what is the balance between gas accretion and black hole mergers in terms of growing black holes over cosmic time? Now, if we take the cosmic average, so we take the mass density of black holes in a representative cosmological volume, accretion is the accretion of gas is what determines the typical mass of black holes. In a sense, if you take the accretion of gas is dominating the mass growth of black holes in a volumetric sense. But then if you look at details, the interaction between black hole mergers and gas accretion becomes more subtle. And it's, in fact, is, at least in the theoretical models that have been developed, there are some examples here, the mass of black holes that is gained through black hole mergers is dependent on the black hole mass itself and increases at high masses. So a black hole like M87 is predicted to have about 50% of its mass gained through black hole mergers, like black hole like Sagittarius A star grew mostly by gas accretion. Now, Sagittarius A star and the Milky Way are a particular case, so if you want to ask me about that specifically, I can say something later. Now, the reason for this is twofold. One is that the most massive black holes live in the most massive galaxies, as I showed earlier, and the most massive galaxies don't have much gas. So these black holes are basically starved of gas, and the only way that they have to grow is by merging with other black holes. Furthermore, since the most massive galaxies live in the most massive halos, you are in a dense environment where many galaxy mergers can occur, and so these galaxy mergers can deliver black holes for merging with the central black hole in the halo. And so that's why we see this evolution with mass of how much black hole mergers influence the black hole growth. So a few words on this particular, on black hole mergers and gas accretion. So black hole mergers is, well, it's my favorite topic really. And it's my favorite topic because it's a very complex physical problem in the sense that it requires information and investigation over a wide range of scales as shown here. And it's been, an intense subject of research in a seminal paper by Bigelman, Blenfron, and Rees in 1980. So the reason for this enormous range in scales is that to see when black holes merge, you have to start with the merger of two galaxies. And to know how often galaxies merge, we have to rely on dark matter halos and dark matter large scale structure, which is something that is determined by cosmology on hundreds of megaparsecs. But then, once two galaxies merge, then the physics that determines whether the merger is successful, what happens there, star formation, the kinematics of gas and stars is something that happens on kiloparsec scale. Now, usually at this point, if if you just care about galaxies, you're done. But if you care about the black holes inside this galaxy, at the center of these possible galaxies, then you have many, many or more orders of magnitude to about milli to microparsec scale before the black holes can actually emerge by emitting gravitational waves. So you see here that there is a wide range of physical scales, but also at each physical scale, you have an associated time scale. So while we're talking about billions of years here, we're talking about seconds in this case. And so this is why it's also incredibly challenged to study this with simulations, because you cannot have a single simulation with all these time steps and time scales involved. But as I said, this is a difficult problem, but many, many people are working on it. And the reason why many people are interested is that there is a potential for much new discovery. So here in this figure, taken from the LISA science case, I show some possible evolution histories of some black holes. The mass is a function of redshift, so black holes are born and then they grow either by merging with another black hole. This is a sudden jump in the mass, or by accreting gas, and this is the smooth evolution of the mass over time. Superimposed to these tracks of black hole growth, you can see the ability of different instruments to detect these black holes. So these contours here show the reach of LISA, which is a space-based gravitational wave observatory that can detect merging black holes up to very high redshift and specifically for intermediate masses that people for a black hole for a relatively low mass massive black holes. Then we have pulsar timing arrays that have been mentioned very often at this meeting that can detect binary black holes with very small separation. And this is for black holes with a large mass and low redshift. And then, of course, we have all our beloved telescopes that can detect all this with photons. And so you see here that the potential for discovery in terms of how black holes grow by combining these probes is really enormous. And if you attended the section multi-messenger science for massive black hole binaries with ngEHT yesterday, you know how this is very exciting. And if you haven't attended those sessions, you can go to YouTube and watch the videos, because you will see how ngEHT, especially for black holes in this mass range, so in synergy with ETAs, can give information that we have only dreamt of until now. Although the probable bottleneck is finding binaries that are within the reach, since we haven't been up to date to find many binary candidates yet. But again, some of the talks given yesterday touch on this. How about gas accretion? So as I said, black hole mergers is mostly a dynamical problem. There is much in there. In terms of gas accretion, the main fight is between the feeding of black holes through gas going towards the center. Again, it's a matter of scales. Remember, well, I think that people in this group know exactly how small the region probe that black hole is compared to the physical scale of the gas. So you really have to, the gas has to find a way to a very small region, and so usually it has to have low angular momentum to get there. But once the black hole is fed, then there is the opposite effect, meaning that the black hole limits its own growth by injecting energy. The same is done to a lesser extent by stars. So stars also emit ultraviolet radiation, and this radiation is in the winds as well, is one of the ways that gas around stars or star-forming region, shown here, or around black holes, can be rarefied, so get low density, can become hot. Now, hot and very low density gas is not very good at feeding black holes. So in some sense, black holes limit their own growth by injecting this energy. So there is a feedback cycle. At the same time, stars also are the cherry on the cake here, modulating as well the accretion on black holes. So the growth of black holes by gas accretion is also not an easy task. and requires a combination of various factors, the feeding from the galaxy and the balance between feedback, so the energy injection from stars and black hole itself. So over time, again, here in simulations, we see the growth of galaxies, the growth of black holes, and how different conditions can lead to different histories, but in general, moving from early initial conditions to what we see today.
5 minutes.
Perfect, thanks. So something that I wanted to highlight here is really the variety of paths of histories that we can have for black holes. Here I highlighted 2. These are extracted directly from cosmological simulations, but there is really a variety that depends on both on the large scale structure, but also on the conditions on small scale. And now I'm getting to the last bit, which I think is in some sense the most exciting, because it's something that has been very hard to measure with different techniques and for many black holes, which is black hole spin. So in the same way that black hole mergers and gas accretion shape the mass growth of black holes, they also shape the spin distribution of black holes, so the way spins evolve over time in black holes. Again, Angelo mentioned this on Monday, so I will not give much details, but when 2 black holes merge, the spin of the remnant black hole can have, in principle, different values, but the typical asymptotic value, if you start from Schwarzschild black hole, you don't have very specific orbital conditions, it's about 0.7, which is, if you have followed LIGO Virgo, this is exactly what they measure. Also, and this is something that I will go back to, spin direction can flip rapidly at the time of the merger. You really have, before the merger, 2 vectors pointing in a 2 different direction, and the new black hole can point in a totally different direction, again, depending on the orbital configuration. When black holes grow by gas accretion, the evolution of spin is also dependent on how gas is accreted on black holes. It can go, the magnitude of the spin can increase and decrease depending on alignment between all these angular momentum vectors. You have here well, forget the jet for the moment, but you have the angular momentum of the black hole, so the spin itself, but also the angular momentum of the disk, and how it connects on large scales. So the connection between the directions of the angular momentum, their ability to align, the accretion rate determine how fast black holes spin up or down. In terms of the spin direction, again, which is something that is not discussed as much, spin direction is also modified by accretion, but on time scales that are much longer than what happens when you have 2 black holes merge. It typically evolves more slowly over millions of years, or at least for black holes of this mass. So what do cosmological simulations tell us about this? So here, this is the evolution over time, or the redshift here, of a very massive black hole, something in the range of mass for M87. Here we show the black hole mass, the black hole spin, and all these red dots are black hole mergers. The alignment or misalignment, so alignment would be at 1 for this angle theta, between the gas that is accreted and the spin of the black hole, and here is the accretion rate. So for this black hole, as I said, it's something similar to M87 living in a very massive galaxy. The last phases of its life, it has very low accretion rate on average. So you see here that there is misalignments between the gas and the black hole, meaning that in principle, the spin should decrease and and modify its direction over time. However, since the accretion rate is extremely low, these processes are not actually effective in changing either the mass or the spin of the black hole. What is determining the spin of such black hole at the end of this, at Redshift 0 today, is actually the sequence of black hole mergers that you have there. For a less massive black hole, so this is about 10 to the 8 solar masses, this picture is very, very different. So in this case, most of the mass is gained by accretion with relatively high accretion rate. Now, in these conditions, we expect the gas to be more aligned overall, to continue feed the black hole on similar with similar angular momentum gas. And there are not many black hole mergers, and they're all with very small mass ratio. So the final spin is determined uniquely by accretion. And so you see here that different pictures emerge. And again, I will focus just 1 minute on the direction of the spins, not only the magnitudes. So here, if we take a galaxy with the angular momentum of the galaxy disk, and this is the accretion disk, obviously not to scale with its own angular momentum, then we can define two more quantities, which is the spin of the black hole and the direction of the jet. So you have all these disks and two objects that may point in different directions. This is from a simulation by Liska et al. Showing that indeed there could be misalignments. And if you look at data, Jenny Green in 2013 used a few galaxies with masers to look at the alignment between jets and accretion disks, finding that alignment, which is shown here, 90%, is the most probable case, but you also have misaligned case. And the same is for the alignment or misalignment between accretion disk and the galaxy. Here, alignment is at 0, so you have most of the cases, again, that are aligned, well, most. On a handful of objects, really, but you also have misalignments, meaning that the direction of the angular momentum can change over these different scales. And so if ngEHT can extend the sample of black holes with spin measurements, both magnitude and direction, and compare with jets and large-scale disks, we can really get very, very important insights on how black holes are fed from galaxy scales all the way in. So I've reached my summary, so hopefully I was not too late. Just to say that, black holes require lots of physical processes to study, and ngEHT, even with local black holes, can help in different ways. And I will stop here.
By the way, I'm not sure I have a way of unmuting anyone here. It doesn't look like I do. So I do see hands being raised, but I'm not quite sure how we can.
Participants can unmute themselves. Just call on them.
Well, the first raised hand was Gopal Kumar.
Hi, can you hear me?
Yes.
Yes.
Thank you very much, Marta. I have a question regarding the PTA visibility. I vaguely remember a paper by Paul and his collaborator talking about the possibility of detecting, supermassive black hole binaries with the rest mass around 10⁻⁻10 or more, up to very high redshift. So, and I remember your plot showing that up to a redshift of 2. Is that a contradiction there?
Yeah, so if you look at the, so Blazar timing arrays can detect a stochastic background, which is expected to be detected soon, and then also individual sources. So first, it's sensitive at nanohertz frequency. So this gives you the mass and redshift of the black holes that can be detected, because this will give you the frequency. The frequency tells you really the masses, and the sensitivity tells you the redshift at which you can go. Plus the masses that are shifted. But in general, the stochastic background is dominated by masses, 10 to the 8 solar masses at redshift less than 2. And also in terms of individual sources, the detections will be dominated by black holes that are close by and with mass a bit less than 10 to the 10. I mean, in principle, you could have higher black hole masses at higher redshift, but it's just that we don't expect them to be sufficiently common.
Okay, thank you.
Let's take another question from Shep.
Hi, Marta. Really nice talk. Thanks. My question is about the spins. It always seems to come down to spin. So how many supermassive black hole spins do you think we know pretty well? I know a lot of that comes from X-ray reflection studies, and the eROSITA satellite is poised to help us there. But how many spins do we need, and how many spins do you think the ngEHT would need to make inroads on this?
You touch on the main point, which is, all the information that I can give you is statistical. So, I run simulations with hundreds of thousands of galaxies, and statistically I get this. But then galaxies are particular. So for instance, again, the Milky Way is, we think that its history is not the average history for black holes and galaxies of its mass. So how representative it is. To be honest, I'm not sure how to answer your question. I mean, I don't have an answer really, but I would say that even a few, or at least for me, that would be great. Specifically, you know, as I mentioned, you know, not only the magnitude of the spin, but the alignment of misalignment with on various scales. These would be incredibly helpful to constrain models of black hole growth that at the moment are in two opposite directions. Either black holes grow and increase their spin, or they grow and they decrease their spin. So even a few black holes will help there.
Okay, thanks. So we're aiming for 10, but hopefully they'll be.
I'm happy.
Okay, I realize there are more questions, but I think we'll have to do them on the Slack that we can discuss on, because I'm afraid the schedule will require us to move to Yuri's talk.
Okay, thank you very much. So I trust that you can see my slide fine, you can hear me fine, so I'll just start.
Yes, please. And I want you.
Okay, thank you. So let me begin from thanking the SOC inviting me to give this presentation, and the most importantly, guys, good luck with the announcement today. Now to the talk. I'm going to discuss today very long baseline interferometry as a key for understanding neutrino production. So this is about the multi-messenger astronomy and what it can give us. Neutrinos. Neutrinos of astrophysical origin are an exciting topic for already quite some number of years. And let me remind you that there are already 2 Nobel Prizes given for astrophysical neutrinos. However, they are given for neutrinos of an energy significantly lower than what I'm going to discuss today. So in this talk, I will concentrate on very high or very high energies between TeV and PeV. And the reason why we are extremely interested in neutrinos of these energies coming to us from space is the following. The only way how we can produce this kind of neutrinos is if we manage to accelerate protons to relativistic energies. So we can produce these neutrinos either through proton plus proton or relativistic proton plus gamma ray photon interactions. All right, so if we learn what is the source, what are the sources of astrophysical neutrinos of these energies, we will be able to locate and then study cosmic super colliders. So we will be able to answer the question or to attack the question how to accelerate massive particles, protons, to relativistic energies. A number of potential sources of neutrino production were discussed through the recent years. Blazars are apparently one of possible this super accelerator, because blazars know how to accelerate at least electrons to relativistic energies. We have observed it almost by our own eyes. Blazars have the machinery in place, so it does make sense to try to check if blazars can also be sources of high energy neutrinos. Observational search. So during recent several years and even earlier, there were numerous attempts to find systematically associations between high energy neutrinos and blazars. In order to do that, most of our colleagues, most of the studies were made comparing, cross-correlating high energy neutrino results with gamma ray data collected by the Fermi Large Area Telescope. And it does make sense because when you produce high energy neutrinos, you also produce gamma ray photons as a result of the same interaction or interactions. So it does make sense to look under this street light. Unfortunately, numerous attempts failed. There are a number of papers, I just show here on the right-hand side a few, which tried it and didn't find any systematic relation. There is one specific exception from these failed attempts. Not systematically, not on a sample of blazars, but there was a very distinct event, so a high energy neutrino coming from the blazar texas from a direction of a blazar O506 has happened at about the same time as a gamma ray flare from this blazar. So the IceCube collaboration has announced the first highly probable association between a blazar and high energy neutrino. The problem here is that, all right, large and effective neutrino telescope, IceCube, located in the South Pole, has observed for 10 years. And for 10 years, it has found only one blazar association. Doesn't look like enough. Here you can see, so this is a blazar, indeed, Doppler boosted, pointed at us. You can see it in a nice image produced recently by Eduardo Ross and his collaborators. We, after learning this story and being excited, as many other colleagues, by this mystery, we decided to approach this problem a little bit differently. We decided to check the following hypothesis, that VLBI-bright AGN prefer high energy neutrino arrival directions. So we decided to go from the VLBI angle. We are not completely nuts. We don't understand that, you know, where are high energy neutrinos, where are high energy photons, and where are we with our radio photons. However, VLBI has two distinct features. So first of all, it can resolve the central parsecs and sometimes sub-parsecs of blazars. So it provides the highest angular resolution, and it can filter for you jets looking at us, at an observer. Okay, so here's what we have done. On this slide, I have summarized to you two different analyses which we have performed. So let's start from what we have on the left-hand side. Regarding the VLBI sample which we are using the so-called radio fundamental catalog, which we were working on with together with many colleagues starting from 20 or 30 years ago, and actually almost 20 years ago we realized that it is such a rich database that we must make the VLBI catalog of blazars complete as possible to a low level of flux density in order to be able to perform different kind of statistical analysis with it. So as of today, we have 3,500 bright blazars selected on VLBI flux density greater than 150 millijanskis, which is complete at about 90% level. And we use this catalog and this sample for our analysis. Now let's go to neutrino side. So here we use IceCube, and in the first analysis, we have concentrated at 57 events observed and announced by IceCube as public alerts with energies above 200 TeV. And the reason why we work with very high energies is because the probability of a neutrino of this energy to be of an astrophysical origin is very high. IceCube estimates, so their statistics gives us roughly 1/2. So it is roughly 50% chance that a high energy neutrino coming from ice cube with these energies will be of an astrophysical origin, and another half is generated in the Earth atmosphere. So here on this plot of the sky, by blue, you see error ellipses of ice cube neutrinos, high energy neutrinos. And we have asked a question, is there anything special about VLBI selected blazars which lie in these circles, in these error circles, error ellipses of ice cube neutrinos? And the answer is yes. We have found out that on average, the blazars which end up in these circles are brighter, are stronger than the rest of the sample. The probability that this has happened by chance is only 0.2%. By the way, performing this analysis, we also had to solve for additional systematic ice cube error, which turned out to be half a degree and agreed very well with independent estimates of ice cube itself. Okay, that is what we have found for very high energy neutrinos. The second analysis which we have performed has used not ice cube alerts, but a probability map, which was constructed this time from all energies, from all neutrinos which ice cube has detected in the range between 2008 and 2015. So it's about 1 million events went into this probability map. So the darker the color in this map, the higher is the probability to have a neutrino source in this direction on the sky. And we have asked a very simple question. Do VLBI selected blazars prefer regions on the sky with the higher probability on this map? And the answer is yes. The chance coincidence of this test is only 0.3%. And some of our colleagues with good eyes even claim that if you look at this map, so the color represents the probability to have, I repeat, a distinct neutrino source in a given direction on the sky. So, and green circles are VLBI selected blazars in a complete sample. So people with good eyes even claim that you can see that these green circles, blazars, prefer not to sit in empty white portions on the sky. If we calculate the joint p-value, the joint probability, so significance of this claim, that VLBI selected blazars are associated with high energy neutrinos is already a little bit better than 4 sigma. So let us ask the question, how many blazars emit neutrinos? So from the first analysis, I can tell you that this correlation is driven by 4 brightest blazars in the sample, which you can very well see on the sky. And I think that many of you know these guys by names, including 3C279 here. And 0506 also went into one of the alerts for sure. You can see it here on the left, but it is not included in these 4 brightest blazars. And if we answer the same question on the basis of analysis of all the neutrinos from 7 years of ice cube observations, typically of much lower energies, more than 70 blazars are associated with neutrinos, but we cannot call them by name. This is a statistical result of statistical analysis. So the claim here is that there can be enough blazars to explain the whole astrophysical neutrino flux. We do not claim that all neutrinos come from blazars, but blazars are enough to explain high energy neutrinos from the sky. Okay, the next question, very interesting question to ask, is when do blazars produce neutrinos? And it does make sense to expect that neutrinos might prefer to arrive during flaring state of the blazars. We know that we observe flares in cores of extragalactic nuclei during the phases when the density of emitting particles goes up in these regions for one reason or another. And we did know from results of radio observations here on this plot, I showed you results coming from Owens Valley and from the Russian Ratan 600. So flux density versus time, that after this very well-known neutrino from 0506, we got this major flare from this blazar. All right. So are neutrinos generally related to jet flares? And here's the answer. So we have produced a stacked variability curve for the blazars which ended up sitting in the error circles of high energy neutrinos from IceCube. And it turns out that indeed for the delay which equals to 0, so for the moment when radio flare, when radio observations happen during the time of neutrino arrival, we do see the flare, right? So the flares which we observe in radio, here we use the Ratan 600 observations, they do prefer to happen during the time when high energy neutrinos arrive. Let me underline here that at Ratan 600 we observe at different frequencies, and this result is observed mainly for the highest frequency of 22 gigahertz. And this is a hint that you do want to go to the highest possible observing frequencies due to opacity effects. The higher the frequency, the closer you see your blazar to the base of the jet and to the central engine. The effect which I'm discussing right now, this coincidence between radio flares and high energy neutrino arrival times, is the strongest for PKS 1502 plus 106. The Owens Valley group even has published an astronomy telegram on this particular event. This result was later checked and confirmed by our colleagues using Owens Valley data and Metsahovi data for their observing samples. Okay, so let me move on and share with you results which we have achieved very recently with other collaboration with other neutrino telescope, the European ANTARES telescope. Let me remind you that ANTARES is effectively 100 times smaller than IceCube. So talking about any statistical significance, we should not expect we shouldn't expect this to be comparable to IceCube. So what we have got from an analysis with ANTARES is the following. That's cross-correlation of a complete sample of VLBI selected blazars with ANTARES neutrinos, provided the p-value of 2%. This is not highly significant. However, we have also performed the so-called search for untriggered flares. So our colleagues from ANTARES has taken our complete VLBI selected blazar sample, and for every blazar, for every direction of a blazar from this sample, so 3,500 blazars, they search for untriggered flares. So they search for moments in time when many flares come one after another. And out of 3,500, they have found 10 most prominent events, untriggered flares, and immediately for 1 out of 10, for PKS 0235 plus 108, we have found the following. So this is the result coming from ANTARES. You see their neutrinos in this time range. We have realized, together with our colleagues from Owens Valley Observatory, that from all their Owens Valley observations, within about 15 years, a major radio flare has happened exactly at the time of this untriggered flare, which was found by ANTARES. And IceCube high energy neutrino also arrived at the same time. And here, the last but not least, the gamma ray flare coming from Fermi. So TXS 0506 is not the only one interesting example anymore. There are more interesting cases. So interpretation, what is going on? So bright AGN produce neutrinos, most probably in relativistic proton plus gamma photon process. Photons come either from accretion disk or the jet base, with energy estimate, like, okay, apparently not very accurate with this huge energy range. Is still a lot of work should be done in order to understand this better. And this requires high energy protons, at least with the energy of an order of 10 to the 16 electron volt. Neutrinos are accompanied by gamma rays. They must be, as you can see here, but no correlation found systematically. Yes. What is the reason for that? We believe that the reason is the following: the secondary photons lose energy to pair production fast, and because of that, they should be observed at significantly lower energies. VLBI selects AGN with small viewing angle, so protons are accelerated along the jet. Neutrinos, which are born by protons, also go in the same direction, are also beamed, and because of that, VLBI basically selects active galactic nuclei, which effectively send neutrinos in our direction. An important note to make is that observed radio and gamma ray photons, as well as neutrinos, can be produced by different mechanisms, even in a little bit different regions in the central parsecs of active galactic nuclei. This mechanism must be related, but they should not be the same. Okay. So current, thank you. Yes, I have 4 or 5 more minutes. Current situation and prospects. So observationally, from neutrino side, either from public data or direct collaboration with different neutrino instruments, and directly collaborating is always the most efficient. That is what we are doing right now. So IceCube continues to observe with plans for a significant upgrade. Baikal GVD, the Russian neutrino telescope, is starting to observe right now. You can see here also the Russian winter at Baikal Lake, and ANTARES is about to become, within the next years, a large KM3net telescope. And let me mention that part of the sky will be covered by old instruments, and parts of the sky will be unique for one or another. So altogether, we will have huge statistics, and we will be able to attack and probe and study different objects of our interest. Talking about VLBI, there are focus studies of blazars of special interest. There are VLBI observations triggered by high energy neutrinos. For example, just yesterday, I have triggered another VLBI monitoring campaign on a recent gold IceCube high energy event alert. And complete blazar samples are being observed right now by the Boston University program, Mojave program PI, Alan Marsher, and Matt Lisser, I guess, are here with us. So this will provide huge data which will allow us to continue this study. Apparently, this is supplemented very importantly by gamma ray observations, by Fermi, and by radio variability coming from Radon 600, Owens Valley, and more radio observatories. So from observations to physics. Right now, we are watching and apparently are enjoying the developing of a new exciting field, which will allow us to address extremely interesting aspects of cosmic neutrino production. So here I list the questions which are important for us. What happens at parsecs, at subparsec scales? Are neutrinos accompanied by flares? If yes, every neutrino or just some of them? Where do these flares happen? Are neutrinos accompanied by changes in magnetic field, in particle density? Where? Is it related to accretion disk region, jet base, farther downstream the jet, in shocks? How and where are neutrinos produced? Is it P plus gamma or P plus P process? How are the protons accelerated? By the central engine, in shocks. How and where are the photons produced, which are required for P plus gamma process? Is it accretion disk? Is it synchrotron self-component from the jet? And here I come to ngEHT. So ngEHT has the highest, or will deliver the highest possible resolution, and at the same time, this will happen at high observing frequencies, which means it will observe in optically thin regime, and it will allow us to see the region of our huge interest, starting from the accretion disk down to the jet. Okay, and now I move to the summary. So we believe that we have strong evidence now that neutrinos from TeV to PeV energies are produced in central parsecs of bright blazars. many dozen of blazars are associated with ice cube neutrinos. Intriguing results are coming from ANTARES and even Baikal GVD. I will answer a question if you're asking about Baikal GVD, don't have time right now. And VLBI jet observations are key to these associations. Future ongoing studies in the exciting multi-messenger era. So let me truly underline this idea. Will allow us to address this new physics on proton acceleration and neutrino production. And we are doing very well right now together with our particle astrophysics colleagues with neutrino instruments, with VLBI, but we need ngEHT to get the highest angular resolution in the most optically thin, transparent regime to truly see what is happening in central regions of active galactic nuclei in the time of neutrino production. Thank you.
Indeed, thank you. I think Avery is both clapping and has a question.
Yeah, thank you. Thank you, Yuri. Thank you, Yuri, for that. It's an exciting talk and exciting prospects for multi-messenger astronomy at very high resolution. One thing that you didn't mention, but seems leap out at me as a natural thing to try to do would be constrain the mass of the neutrino just by looking at time delays. The fact that the neutrinos are arriving either at the same time as the high energy gamma rays or beforehand places an obvious mass limit, which my back of the envelope guesstimate during your talk suggests is actually quite competitive. If it's coming from.
My many years of experience talking with you have proven that you're extremely optimistic theorist. So unfortunately, even though I am supposed to be optimistic as well, we did make this estimate as well some years ago, actually a couple of years ago when we got our first results. And the accuracy within which we measure this delay is by far not competitive to accuracies which you can get on the ground. So using the ground experiments which constrain the neutrino mass. So unfortunately, in order to be able to do that, we need to have many orders of magnitude higher accuracy of measuring the delay.
Okay, well, that's that. Thank you.
Great. And I believe the next question is from Koichi, please. You are muted. You have to unmute first.
In low luminosity AGNs, the electrostatic potential, the electrostatic acceleration potential around the black hole is of the order of 10 to the 16th electron volt. Because
I didn't understand the question.
Well, to explain proton acceleration, I think magnetospheric electrostatic acceleration in the vicinity of supermassive black holes in low luminosity AGNs is one of the plausible mechanism to accelerate protons up to 10 to the 16th electron volt, because their electrostatic potential gap is of that order, around that order.
I understand this is a comment, right? So let me reply with another comment that we have considered options on how to accelerate protons, and the mechanism which just right now with the data which we have, we prefer is accelerating them in shocks, which okay, let me try to go back in my presentation. So this is a very wonderful cartoon which is used and shown in presentations very often, done some years ago by Alan Marsher. And so here you can see that the observed base of the jet, so what we call the core, might be either the core itself or close to the core, might be standing shock. So our estimates have shown that protons might live long enough in this shock to get accelerated to this kind of energies. But it is just our back of an envelope estimate, and apparently this requires many more experimental data to be able to precisely answer the question of what is the preferred mechanism of protons acceleration.
So magnetospheric acceleration could be an alternative way of producing such energetic protons, I think.
Appreciate that, understand. Thank you for the comment.
Thank you.
Let's take one more quick question from Sritan, and that'll be the last one.
Hi, thank you. I wanted to ask, how bright does one expect these objects to be in, 230 gigahertz? And this would also require the triggering possibility. Is that right? Thank you.
Yes, so we have discussed requirements for studying, so to introduce this multi-messenger astronomy case into ngEHT yesterday, and we have discussed that it will require a possibility for a trigger. We believe that a one-day trigger will be good enough to attack this problem. But your another question was, I have already forgotten.
How bright are they?
Yes, how bright, yes. The answer is very simple. You have heard that one of the targets which we have immediately selected from our first study was 3C279. So ngEHT has, sorry, EHT has already observed 3C279. So apparently the deeper the better, because as we discussed yesterday, it is important not only to get the signal, but also to be able to put a stringent upper limit in case if we get high energy neutrino from a given blazar, but we do not see anything happening in radio waves. So if you detect it, then actually the sensitivity requirements are quite all right, quite benign. But if you want to also be able to tell, all right, we have cases when there is nothing happening around the accretion disk in the base of the jet, then you want to go much deeper. But we have discussed the numbers yesterday, they are in the files.
Wonderful, thank you.
Thank you.
Great, thank you. This has been a good session. Thank you to the speakers. And I believe now we have a coffee break.